Okay, so this is unit or unit 5.2, and right, we're going to talk about detection of radioactivity. So radioactivity, you know, exists all around us, right? It's called background radiation, as you can see, right? And it can be both natural and artificial depending on where you are, right? There is natural radiation all around us. This pie chart shows, right, the majority of the radiation you detect is in the air. Then there's cosmic rays, which are coming from the sun. Rocks can be radioactive, some food can be radioactive. There are medical uses, right, which is not, and nuclear power station and nuclear bombs, right? So this is not something you normally come across. This is obviously isolated, and this is unfortunately something that the world has experienced and still, anyway. So radioactivity was discovered in 1896 by a French scientist when he saw, when he was working with uranium, and he saw that it affected photographic plates when they were wrapped in black paper. So he saw that they were like, some spots on the photographic plate, and that ionized gas. Later, the scientist Marie Curie discovered the radioactive element radium, which also led to her demise later on because they weren't cautious about the handling radioactive material. And so she had radium lying in her you know the drawer of her work table, her desk, just like that. Like we have peanuts for snacking, she had radium.
Yeah.
And we now know that radioactivity arises from unstable nuclei which may occur naturally or be produced in reactors. Right, so what are the
But like,
hmm?
oh yeah,
Go
it's
ahead.
written. No
Okay.
problem.
So we're all exposed to radiation, and by and of itself, it's not a bad thing. I mean, given the amounts, right? If you're like super exposed, then that's an issue. But otherwise, right? So cosmic rays, these are high energy particles from the sun, are mostly absorbed by the atmosphere. Some of them reach the Earth's surface. There's radon gas in the air, which is very, 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 very low in percentage. It's like negligible mostly, but it's there. Numerous home appliances, particularly in Scotland, are built. Sorry, not appliances. Sorry, numerous homes are built from granite rock that emit radioactive radon gas, and this can collect in basements or well-insulated rooms if the ventilation is poor. So that could be problematic. You got radioactive potassium 40 in food, and that is absorbed by our bodies. Now they say that as if like, oh my god, right? We got radioactivity in your food. I mean, let's talk about the abundance, right? Just like we talked about chlorine, there's radioactive carbon as well, right? So I mean, the amount is not something that's worrying, but it is telling you, yeah, it's there. Various radioisotopes are used in certain medical procedures, and radiation is produced in the emissions from nuclear power stations and in fallout from the testing of nuclear bombs. The latter, which means the nuclear bombs, produce strontium isotopes with long half lives, which are absorbed by the bone. And that's why, in areas where there is nuclear fallout, it is uninhabitable for very long times because it has long half life. So radiation is going to exist, or persist, not exist, but persist over there over long periods of time. Then, ionizing effect of radiation, right? So what does that mean, ionizing? So the radiation can cause cause the formation of ions. So there's a device called an electroscope, right? It was charged. A charged electroscope discharges when a lighted match or a radium source, right? So that's radioactive, is brought near the cap. Why does that happen? So they've illustrated that here, right? This was charged, the cap. They're putting a match near it. So what happens with the match? The flame knocks electrons out of the surrounding air molecules because obviously you're providing heat and that's energy. And so when electrons are knocked out, it becomes the ions are formed, positive ions are formed. right? Air molecules have lost one or more electrons. In the second case, right, this guy is charged and you're bringing a radium source, sorry, near it. And so the uh, radiation causes the ionization as well. So positive ions are right, and so the same kind of electrons are knocked off and everything. So the positive ions that are formed are attracted to the cap if it is negatively charged. So we are forming positive ions in both cases. The cap was negatively charged. They attract, they neutralize, right? The charge is lost. If in case the cap was negatively charged. If the cap was positively charged, the positive ions will repel, but the electrons will be attracted. Either case, the charge is neutralized. Okay. Note that if a neutral atom gains an electron, it becomes a negative ion. So you're losing electrons, become positive ions, gaining them, you become negative ions. Yeah, we know that. So that is, ionization. Like ions are formed, right, in the air. Now, the Geiger-Müller tube or the GM tube is a device to detect radiation or the ionizing effect of radiation. So the ionizing effect is used to detect radiation when radiation enters the Geiger-Müller tube, either through a thin end window made of a material called mica. Right, so it's illustrated over here. This is the Geiger-Müller tube. This is the window at the front, and there's argon gas inside, and then there are wires, and they're connected to right, they're showing the internal circuit. Over here, there's obviously inside a box and a meter and a display. So they either enter through the wall, or if the radiation is penetrating, which means it can get through stuff, through the wall, So either through the window or the wall. And what it does, it creates argon ions. Now, argon is from the noble gas family. It causes the ionization of argon, right? So these guys don't take part in any reactions. We know that, right? They are very stable. They have full valence shells. It causes ions to form for these guys, right? So it creates argon ions and electrons. These are accelerated towards the electrodes, right? So the electrons which are negatively charged will move towards the anode, and the positive ions will be towards the cathode and cause more ionization by colliding with other argon atoms. So right on the way they collide with other atoms, they cause those to further form ions, and so more ionization occurs, right? On reaching the electrodes, the ions produce a current pulse which is amplified and fed either to a scalar or a rate meter. What's the difference? A scalar counts the pulses and shows the total received in a certain time. A rate meter gives the count per second or count per minute or count rate in general directly. So a scalar gets the pulses and then shows that. A rate meter does it directly. It usually has a loudspeaker which gives a clicking sound. So I don't know if you've ever seen this in movies or cartoons, but they have this device with a probe type thing, and they move it around and it gives like a sound of noise. Have you ever seen that?
I think so,
Like
yeah.
not quite like the noise I tried to produce, but like a squeaking noise,
Oh, okay, okay.
squeaking cracking noise. Count rate corrections, what does that mean? So we talked about background radiation, right? So if you're in an area where the background radiation is considerable, it's high, and so standing away from any source of radiation that you want to measure, you first take an account of the background radiation. So you note that, and then when you are measuring the radiation from the source, you're going to take into account, okay, fine, so the reading I'm getting is not from the source only because the background radiation is also there. And so you subtract the background radiation count from whatever you've noted from the source, and that is a corrected value. Kind of like zero error we did way back when.
Yeah, I think, yeah.
Okay, kind of like that. Are you following so far? Yes?
Yeah. Yeah.
Haram, are you following?
Yes.
No?
Yes.
Yes. Oh, you had me concerned for a second or two. Okay, now the three types of nuclear emissions. Right? You must have heard of these guys, the alpha, the beta, and the gamma radiation. Right? So they talk about an experiment over here to detect the three different types of radiation, right? And they talk about the setup, how to do that. The emissions of radiation from a nucleus is a spontaneous and random process in direction. Okay, so we'll talk about that later. So it's a so this happens spontaneously. You can't control it, right? And right, they're affected by magnetic and electric field. And you can stop them by either a sheet of paper or a sheet of aluminum or a sheet of lead. So, right, this experimental setup that they're talking about, right, we're going to just go through each of these and they'll mention that. So, alpha particles of the first kind. Zoom in a bit. So, these guys, what they are basically a helium ion. So, helium has two electrons, right? And so it also has two protons and two neutrons. So, it has a proton number of 2 and a nucleon number of 4 or a mass of 4. What alpha particles are they are basically helium ions that have lost both their electrons. So they just basically have a +2 charge. They're two protons and two neutrons. Okay, that's
Yes.
what they are. Right now, why are they called alpha particles? They are because they have certain properties, and also, right, the fact that you don't normally get helium ions, because just like we talked about argon in the Geiger-Müller tube, right? Helium's a noble gas. It's not doing anything. So when this happens, it's like, okay, that's not normal, I guess. So, right, these guys are stopped by a thick sheet of paper and have a range in air of only a few centimeters. So this is called penetrating. They're not very penetrating, so they don't get very far. Right? They have a lot of kinetic. They have the most kinetic energy of the three, alpha, beta, and gamma. Right? But they're slow. Why is that? Because they cause the most ionization. So they have frequent collisions with gas molecules and they cause the molecules to become ions, which is ionization. So they cause a lot of ionization. So they have the highest ionization strength, right? But the lowest range, and they're slow, right? But they do have the most kinetic energy. And so that kinetic energy is what's causing the ionization. They are deflected by electric and magnetic fields, which makes sense because they're two protons. So they are going to be affected by electric and magnetic and strong magnetic fields in a direction by an amount which suggests that, right? So this is where they figured out that they're helium ions, right? Through various experiments. For a particular substance, they are all emitted with the same speed. Depends on the substance that is emitting them. So they don't have like a fixed speed. Depends on what is the source of the alpha particles, but generally it's like 1/20th of that of the speed of light. Okay.
Yes.
And then they give you example of americium, right, which is a radioactive element. It is a pure alpha particle source. So, right, it emits only alpha particles and it has uses in smoke detectors, which are mentioned later on. Then you've got the beta particles, right? And these guys are basically a beam of electrons. They can be stopped by a few millimeters of aluminium. They have more range, they can travel several meters in air, but their ionizing power is much less than that of alpha particles. They can also be deflected by electric fields and by easily by magnetic fields. So you don't, why did they mention easily deflected by magnetic fields? Because for the alpha particles, it mentioned it needed strong magnetic fields. So this guy can be deflected easily by magnetic fields. You don't need as strong a magnet. Measurements show that beta, you see it's written beta minus. The reason why it's written minus are streams of high energy electrons, because electrons are negatively charged, transmitted with a range of speeds up to that of light. So a range of speeds, the maximum can be the speed of light. Strontium 90 emits beta particles only. Note that beta minus particles, I've been reading about beta particles, but beta minus particles, a beta minus particle is often just referred to as a beta particle. So you're not really paying attention to the minus over there. Okay, the deflection of the beta particle by a magnetic field can be shown by this experiment. So you got a strontium source, it's going to emit only beta particles, and then you got this magnet over here and the Geiger-Müller tube and the counter. And so you see the dotted line going straight, and so the count is going to be very less. Why? Because most of them are being deflected, right? But if you place the tube over here at point B, you're going to get a higher count rate. Okay.
Okay. Yeah.
Then you've got gamma emissions. These are the most penetrating, so they have the least, ionizing effect, right? But they travel the furthest, and not just the furthest, but they can actually travel through materials, right? So alpha particles can be stopped by paper. Beta particles cannot be stopped by paper, but you need a few millimeters of aluminum. These guys need a few centimeters of lead, so they need that kind of layer to actually stop them. Otherwise, paper, clothes, other stuff, they're getting through. They ionize a gas even less than beta particles and are not deflected by electric and magnetic fields. And the reason why is because gamma emissions are basically electromagnetic radiation. Right? If we just take a quick peek over here at the electromagnetic spectrum, see these guys?
Yeah.
So the gamma radiation is part of the electromagnetic spectrum. And so it's not affected when you put it in a electric or magnetic field, because it has both electric and magnetic fields itself. Right? They give interference and diffraction effects, which is something you like, they're just mentioning, but you'll come across this in A-level physics if you choose to take that. And right, and that's basically something that is a property of waves. Interference and diffraction are properties of waves, and so these are waves, they're electromagnetic waves, right? And they travel at the speed of light. Their wavelengths are those of very short X-rays, from which they differ only. So they differ from X-rays only because they arise in atomic nuclei. So that's the source. Gamma rays arise from atomic nuclei, whereas X-rays, as we talked about earlier, arise from the change in energy levels of the electrons. Okay. So
Yes.
that is a difference. Cobalt 60 emits gamma radiation and beta particles, but if you cover it up with aluminum, because you need a few millimeters of aluminum to stop the beta particles, so just cover it up with aluminum, and so it's going to stop all the beta particles, and then you're going to get a pure gamma radiation source. Following?
Yep.
Right, now comparing these guys, right, this is basically sort of putting everything that we learned together, so you can read that. Okay.
Okay.
uh, the behaviors over here, the behavior of the three kinds of radiations in a magnetic field is summarized in this figure. The deflection, not to scale, so this just to illustrate, are found from Fleming's left-hand rule, right? So your forefinger is the direction of the magnetic field, your second finger is the direction of the current, which in this case is the direction of the particle, and the thumb is the direction of the force being applied, again on the left hand, right? And so for the alpha particle, the magnetic field it's a positive magnetic field shown, and so it's going into the paper, and so your forefinger is pointing away from you. Do you need me to switch on the camera?
Um, sure.
Sure. Is it working?
Still can't see. Oh yeah, now.
There we are. Right, so magnetic field going into the paper, so it's pointing away from you, right? As for the alpha particle, it's positively charged, so that's the current going to from left to right, and so the force being applied is upwards, and that's what you see. The deflection of the alpha particle is upwards.
Yeah.
For the beta particle, magnetic field is still this way. The beta particle is negatively charged, so it is the opposite of conventional current, and so you flip it around.
Okay.
All right, let me just say, adjust my fingers. Okay, so that's the direction from right to left. We did this earlier.
Yeah.
Right, and so the force being applied is downwards, and you can see that deflection.
Yeah.
And the gamma ray just passes through because it's not affected.
Okay.
Okay.
Yep.
Yeah. Then if you put these guys in an electric field, so what would you expect? Gamma rays against nothing happens, right? The alpha particle in this case is being deflected downwards. Why? Because the electric field is from positive to negative, and because this guy is positively charged, it will be repelled by the positive plate towards the negative plate, right? The beta particles are negatively charged, so they'll be repelled by the negative towards the positive. The alpha particles repelled more strongly. Why? Because they have a double positive charge, while beta particles are high energy electrons, right? So the amount of deflection comparatively is less. Okay, and gamma emissions, again, they're not affected. Then you've got particle tracks, these guys. Okay,
Okay.
so the path of particles of radiation were first shown up by the ionization they produced in devices called cloud chambers. When air containing a vapor alcohol is cooled enough, saturation occurs, right? So it becomes like really close together, the vapor particles. If ionizing radiation passes through the air, further cooling causes the saturated vapor to condense on the ions created. The resulting white line of tiny liquid drops shows up as a track when illuminated. Right, so this is showing the path of the radiation because of the condensation on them, on the particles. In a diffusion cloud chamber, this guy, alpha particles showed straight tracks. Oh, sorry, uh, this guy for alpha particles. These are for beta particles. They're both cloud chambers. So alpha particles showed straight, thick tracks. Very fast beta particles produce thin, straight tracks. So maybe this dotted line over here. While slower ones gave short, twisted, thicker tracks. So all these squiggly lines you see. The ejected, where was it? Gamma emissions eject electrons from the air molecules. The ejected electrons behave like beta particles in the cloud chamber and produce their own tracks spreading out from the gamma emission. Okay, so stuff for you to know. The bubble chamber, in which radiation leaves a trail of bubbles in liquid hydrogen, has now replaced the cloud chamber in research work. The higher density of atoms in the liquid gives better defined tracks, as shown in figure 5.2.9. So that's over here. A charged particle track and a bubble chamber. Looks nice.
Yeah.
So, where was I? A magnetic field is usually applied across the bubble chamber, which causes the charged particles to move in circular paths. The sign of the charge can be deduced by the way the path curves. Right? And so the way that curves, yeah, is this. Right? What magnetic field is being applied, what charge is the particle. So if it's going into the page, if it's curving in an anti-clockwise motion, then it's an alpha particle. If it's curving in a clockwise motion, then it's a beta particle. If it's not doing anything, it's a gamma particle. So in this case, what we notice, I don't know whether this is spiraling inwards or outwards. I think this is spiraling inwards. So this is clockwise, I believe. All right, you shot it in here. And so there we're going. And so this is most likely a beta particle.
Yeah.
It
Okay.
will be alpha or beta.
Seems to be beta,
Okay.
right? Because you see it's coming in from here, from the middle lower part of the image, and it's going and
Yes.
it's moving in a clockwise direction, assuming that the magnetic field is going into the page. That is an assumption, right?
Okay. Yes.
So yes. Now what we're left with is radioactive decay, and right, some stuff like I'm telling you beforehand, uses of radioactivity and safety. So there's all that, and then safety precautions is something that I'll most likely leave for you to read. Depends on how much time we have. So tomorrow's class, we are going to talk about radioactive decay, right? And with that, we're going to talk about half-life and measuring half-life. So nuclear stability, half-life, the decay curve, right? Experiment to measure half-life, and yeah. So if we have time left after discussing all of this, then we'll just take a look at the uses of radioactivity and safety precautions. Otherwise, I'll leave that to you. So tomorrow we're going to be done with section 5 or unit 5, and next week we'll get to the last unit of the syllabus, space physics. Okay.
Yes.
Okay.
All right. So I will see you guys tomorrow, inshallah.
Okay.
Yes.
Allah.